So let's take a look at this conceptual example just to get more familiar with some of the symbols. Here we're going to have a real EMF source right here. It's going to have its EMF written right there. It's going to have its internal resistance right there, the little r. And we might want to hook this guy up into a circuit. We can measure the potential across the battery terminals by taking our voltmeter and measuring it right there through points A and B. So here we're measuring the potential. And then we can also want to be able to measure the flow of current. So we're going to take our ammeter and say that current is going to be flowing in that direction. It's going to be flowing towards the negative terminal right here. And we can measure the current flowing through it. So now let's take the setup from the last slide, have the same battery, same resistance and voltage, and now hook up a resistor to it. What's going to happen is, as I said, I have my positive side over here. My current is going to flow from my positive side through this resistor here into my negative side. And what we're interested in is what is the current measured by the ammeter, and then what is the reading by the voltmeter. Or so what is VAB? Well, to solve this we need to write Ohm's Law, and I'll give you a heads up that I'm doing this a little bit differently than the book to give you another method here. Is the voltage potential is equal to current times resistance, and this is going to be the total resistance of the circuit. This total resistance right there is going to be the sum of this 2 ohm resistor plus that 4 ohm resistor. So the total resistance is going to be 6 ohms. We can solve for current. That's going to be equal to the voltage, the potential, divided by the resistance. So my 12 volts divided by my 6 ohms. All I've done is I've rearranged this equation right here. And I can say that my current is now going to be equal to 2 amps. So I've solved for my current. Now what we have to realize is the same current is going to be flowing through that resistor, same as that resistor, and same as this ammeter, which I forgot to mention has no resistance to it. So we can write Ohm's Law for just this battery right here. We can say the voltage in the battery, VAB, that's going to be equal to the current multiplied by the resistance, and that's actually going to be the current multiplied by the little resistance of the battery. So it's going to be the 2 amps multiplied by 2 ohms, and what we're left with is we're left with 8 volts. So kind of what's happening right here is this little resistor right here is eating up 4 of the volts from the EMF of the battery. Now we've gone ahead and we've moved the voltmeter, taking a look at this voltmeter right here, and we've already solved for the current flowing through this guy. We said the current flowing through this must be equal to 2 amps. Same amount of charge is going to flow through this 2 ohm resistor as through this 4 ohm resistor. So the current right here is also still going to be 2 amps. We can apply Ohm's Law for this voltmeter and say voltage is equal to current times resistance. And so the current must be 2 amps. The resistance is now 4 ohms. So the voltage here must be equal to 8 volts. We get a warm fuzzy feeling about this 8 volts because we got 4 volts because we had 4 volts here in the internal battery. 4 volts plus 8 volts is going to give us the 12 volts of EMF, the 12 volts of energy that we initially had. Remember, energy cannot be created or destroyed. The last setup right here is we have our power source, and it's going to be going through the ammeter, through the resistor, and now through the voltmeter. Voltmeters are designed to measure a potential difference. They're not designed to have things flow through them. So this is a big fat no-no. Essentially it has no internal resistance, and the current will flow freely through the voltmeter, essentially frying it. And lastly, we have an example where we have the same battery and we have no resistor down here. We have no resistance. So what we can do is we can write Ohm's law. V is equal to I times R. Therefore, I is going to be equal to the voltage divided by the resistance. This is just going to be the internal resistance of the battery. So before it was R total. I had 2 resistors, now I only have 1. And so I'm going to have my 12 volts divided by my 2 ohms. And I'm left with a current of 6 amps. So that's what my current is going to be flowing through the ammeter, 6 amps. What is the voltage going to be? This is going to be 0, because essentially this resistor right here is going to eat up all 12 volts right here. One thing to be very careful of when you're hooking up batteries and such is that very typically this resistance is a very small number. So if you hook up a circuit and it has no load to carry down there, then you can get obscenely large currents flowing through that, greatly exceeding the current limitations on wires, and so wires will tend to melt. So let's take a look at the same circuit that we've been talking about here. What we typically do when we talk about an EMF is we'll say all 12 volts are going to be here on the positive plate, and then the negative side terminal is going to have a voltage of 0 volts. What we can then do is we can say, okay, we know that for the circuits in this chapter, the current is going to be equal to a constant across the circuit. So once I've calculated out what my current is, it's going to be the same across each resistor. Then what I can do is I can say, well, what is the voltage drop going to be across each resistor? The voltage drop across each resistor is simply going to be equal to the current flowing through it multiplying by the resistance of each resistor. So what I can do is I can kind of graphically work my way around this circuit. Say I'm going to start right here, and I'm going to say that my voltage right there is going to measure to be equal to 12 volts. Let me work my way through to this resistor right here. That resistor is going to cause the voltage to drop. It's going to cause it to drop by the current, 2 amps, multiplied by the resistance, 2 ohms. It's going to cause an 8 volt or a 4 volt voltage drop across the resistor. So if I measured the potential at that point, it would be 8 volts. Then the circuit is going to continue to flow. It's going to hit that resistor right there. It's going to cause a voltage drop which is equal to the current multiplied by the resistance, current 2 amps, resistance 4 ohms. It's going to cause an 8 volt voltage drop, and the potential will drop down to 0 for the return trip and reach the 0 volt terminal right there. Since we've been talking about potential, or potential energy if you will, we can talk about the rate at which energy is delivered to or extracted from a circuit element. That's going to be the power. Remember, power is energy per unit time, and that's going to be related to the potential across it, as well as the current flowing through that. And of course, we're talking about power, or power energy per time. That's going to have the unit of watts, coming back to haunt you. If we're talking about a very pure resistor, also could say a very ohmic resistor, we could use Ohm's law and say V is equal to I multiplied by R to write the power as such, or we can rearrange it in the language of the current and write it as the voltage squared divided by R, whichever is most convenient for us. So we can go back to the circuit that we are currently beating to death, and we can say this source right here, how much power can it possibly deliver? Well, the power it can deliver, we know that it's going to be delivering 2 amps worth of power, and we know that the EMF is going to be 12 volts, and so all I've really done is I've said power is equal to current multiplied by potential. So we have 24 watts of power available to the circuit. What does this resistor here eat up? Well, it's going to, we can say that the power is going to be the current squared multiplied by the resistance. The current is going to be 2, it's going to be squared. Resistance is going to be 2 ohms, and so we're left with 8 watts being eaten up by this resistor. How much power is being used by this resistor, well, we can say the same thing. Power is going to be current squared multiplied by the resistance. And so the current is going to be 2. The resistance is going to be 4. Make sure we square the 2. And we get 16 watts of power being eaten up by that resistor. And so if you think about 16 watts used by that resistor, 8 watts used by that resistor, 24 watts available to the circuit, it all adds up. So energy is definitely conserved. Let's take a quick look at our short circuit where we had 6 amps flowing through the ammeter and we're flowing through just the 2 ohm resistor. We again say power is equal to current squared multiplied by the resistance, and so that's going to be 6 squared multiplied by 2, or 36 multiplied by 2. So 72 watts of power. This is another reason to say why short circuits are dangerous, is because that's about the same power rating that you'll see on a light bulb. This battery is going to get hot very, very quickly.